Entropy. Entropy S is another macroscopic property of a system. We have another macroscopic properties such as temperature, volume, pressure, and so S is just one more. And mathematically, we can find entropy by dividing heat that flows into a system, Q, divided by the temperature of the system. And units of entropy is joules over Kelvin. Let's look at this diagram. We have two systems, system 1 at temperature T1 and system 2 at temperature T2, and assume that T1 is larger than T2. So then heat flows, obviously, from hotter to the colder this way, as an arrow. Then change in entropy for system 2 is amount of Q that flow into the system divided by the temperature as T2. At the same time, system 1 is also experiences change in entropy, delta C1. It loses amount of heat Q, so it is minus Q over temperature 1, that is temperature of a system 1. The total entropy change is 0 for all reversible processes. The total energy change is positive for all irreversible processes. That means, if you think about it, delta S is equal Q over temperature of the system, and that means the heat is flowing into the system. Using entropy, we can reformulate the second law of thermodynamics. It states that in any thermodynamic process, delta S universe, so change of entropy of the whole universe, is always positive or equal 0. All three statements of the second law are equivalent, and each one of them can be used to prove the other two. Each version gives different insights into the meaning and consequences of the second law. Let's talk a little bit more about entropy. In microscopic terms, entropy is a measure of the amount of disorder or randomness in the system. You might have heard this definition somewhere. So entropy is equal disorder of a system. Increasing the temperature of the gas or liquid increases the kinetic energy of the molecules and increases the amount of disorder. And think about crystal, that is ice, and everything is organized and doesn't go much anywhere, it just sits in its corners of the crystal. But then if you increase the temperature and ice became a water eventually after it melted, molecules of water have way more freedom, so they can be in many different positions, so it becomes way more disorganized, so entropy increased. Adding heat to the system always increases its entropy. Let's consider a system of gas molecules in a box and ask how the molecules are distributed. For the simplicity, we would divide the box on two parts, right and left part. And N will be a number of molecules. So if we have one molecule, we have only two possible states. Molecule is on the right or molecule is on the left. So we have only two possible states. Probability of finding the particle on the right side of the box is then equal 1 over 2. The same as probability to find particle on another side of the box. This is right side and this is left side. It's also 1 over 2. Let's now consider a case when we have two molecules, 1 and 2. In this situation, the first combination is represented here with both of them on the left-hand side. Then another possibility is 1 on the left side, 2 on the right side. Then 2 is on the right, 1 is now on the right side and 2 is on the left side, and now both of them are on the right side. So total possible state, we have four states, and 2 of them are with equally distribution on the right and on the left. If we add another molecules to the case, That means we'll choose n equal 4. The number of states increases dramatically. Now we have 16 possible states, and you can analyze those pictures forever as well by yourself. What I want you to notice that the number of states where molecules are evenly distributed are actually the largest number of states. Let's just count. A total is 16, so this is equal distribution. This is equal distribution. This is equal distribution. This is also equal, and this one's equal, and this one equal. Let's count. 1, 2, 3, 4, 5, 6. The probability that we have an even distribution of the molecule on the right side and on the left side is 6 over 16, approximately 0.4, or to be exact is 0.375. So, to repeat, one molecule would have two possible distributions. The probability of finding the molecule on one side is then 1 over 2. With two molecules, there are 4 possible states. With 4 molecules, the possible state increase rapidly. And a key assumption of thermodynamics is that each of the states is equally likely. Let's now plot this probability. And what we're plotting here is we're plotting number of particles in the left part of container, and what is probability to have this exact number of particles on the left side of container. And what we can see, we can have only one case when all particles are on the right side, and that means probability is 1 over 16 for this point. And the same part is over here, is 1 over 16 when we have all particles on the left hand side. For this particular point, if we count cases, we're going to have 4 over 16, so 0.25, and this one is already said, it is 6 over 16 for this step. If we increase number of molecules, the shape of the curve will remain, and eventually it will become this very nice peak of the molecules. And the most likely state has the highest probability, and that means this one is the highest probability where molecules are almost evenly distributed on the right and the left hand side. This is how it is connected to entropy. So the most likely state has the highest probability and the greatest entropy. Let's solve the problem 47. So we have 7,000 joules of heat flow out of the house that is at 293 Kelvin to the outside environment at 273 Kelvin. Find the change in entropy of the house, the change of the entropy of the environment, and the total change of entropy of the universe. Is this process reversible or irreversible? Okay. So what's given in this problem? We have 7,000 joules heat flows out of the house, that is at the temperature, so it's system 1. Let's do system house, 293 Kelvin. To the outside environment, temperature outside is 273 Kelvin. So this is flows from here to here. This is where 7,000 joules goes. Find the change entropy of the house, change of entropy of the environment, and the total. So change of entropy in the house is Q divided by temperature of the house. Because heat leaves the house, we have negative sign. The 7,000 divided by 293 Kelvin joules. So we would get approximately negative 24 joules over Kelvin. What happens with the environment? Environment outside is receiving heat, so it should be positive 7,000 joules over temperature of outside 273 Kelvin. So the value is approximately, be correct, here's approximation, is 26 joules per Kelvin. So this is entropy entropy, change of entropy outside, and this is change of entropy of the inside. What is the change of the entropy in the universe in this case? So we have change of entropy in the universe is going to be equal change of entropy in the house plus change in entropy of the outside. So it is minus 24 plus 26. It is plus 2 joule over Kelvin. So what happens over here is that, well, it is approximate. And since the total entropy change is greater than 0, this is irreversible process. So the process is not reversible because this is not 0. And also I want to point it out that entropy of the universe increased. It did not decrease. That it can't according to the second law.